Now we know that the lens of the camera creates a continuous optical image on the image plane. And at this image plane sits your image sensor, which converts this continuous image into a discrete digital image. So an important question is, how densely should we sample the continuous image so that we don't lose important information in it, and at the same time not introduce any artifacts or undesirable effects in the final captured image. So that brings us to sampling theory. So first, let's take a look at how we go from a continuous image to a digital or discrete image. We're going to do this in 1D. So here is your continuous image formed on the image plane by your lens. And this is going to be sampled so as to get this discrete signal that you see here, digital signal that you see here. And so the question that we're interested in is how densely should we sample this continuous image? What should be the distance between consecutive samples? So let's take a look at a very simple signal here, a sinusoid, and a higher frequency version of it right here. And let's say we sample both of these with the same sampling frequency. So these are the samples. In this case, if we apply something like linear interpolation, you end up getting something like this. And you get a reconstructed signal that looks very close to the original signal. Not much damage has been done. However, in this case, you see that you end up getting a flat signal here, a constant. All the information here is lost for all practical purposes. And this is called aliasing because you've undersampled this signal. In fact, there are cases of aliasing where you might introduce new frequencies in the signal, new artifacts, which don't even exist in the original signal. This is why sampling is really important. This is how it manifests in images. So here is an image that is well sampled, and you see that everything looks fine. It's a brick wall with some high frequency texture on it. And when you undersample it, essentially use a sampling frequency that is slightly less than in this case, you end up with these patterns here, artifacts, these waves, this sort of ripple effect, moire type of patterns. And this is called aliasing. This is a visual manifestation of the effect of aliasing, which we're going to discuss. So we want to develop a theory of sampling. We start with our continuous signal here, f of x. And the way this is sampled is by multiplying it with what's called an impulse train. It's a train of delta functions. This function is called the Shah function. We'll call it s of x. You can see the Shah function is a sum of delta functions which are displaced by x0 with respect to each other. So your sample function is fs, which is f multiplied by s. Now let's take a closer look at the Shah function itself. Here is your Shah function, the impulse train. It turns out that the Fourier transform of the Shah function is also a Shah function. It is an impulse train, where if the original Shah function has a sampling period of x0, the Fourier transform of the Shah function has a period of 1 over x0. So now let's take a look at what happens when you sample a continuous signal in Fourier domain, in frequency domain. So you have fs equal to f times s. That's a multiplication here, which is f times the impulse train. In Fourier domain, you have fsu is equal to f of u convolved with s of u. Because we know that multiplication in spatial domain is equivalent to convolution in Fourier domain. So you have f convolved with this Shah function or the impulse train right here. So what does this do? So let's say you have a continuous image and you take its Fourier transform. And let's say that happens to look like this. This Fourier transform is being convolved with the Shah function, the impulse train right here. So what's that going to look like? Well, we know the sifting property of the delta function. We know that if you convolve any function with a delta function, you're going to end up reading out that function itself. You get the function itself. So here you have a train of delta functions. If you convolve that with any function, what do you end up getting? Where you get multiple copies of the original function. So you get multiple copies of f, where the spacing between these copies is 1 over x0. So this is good news for us. All we want is this. We want one copy, but now we have multiple copies of f. And as long as u max, which is the maximum frequency in f right here, is less or equal to 1 over 2 x0, that is half of this distance, you're going to make sure, you're going to know for sure that these copies don't overlap each other. You're going to get these non-overlapping copies. And you can imagine that since you want to recover your original signal, you can actually go in and cut out one of these copies and find the inverse Fourier transform of it, and you can actually recover the continuous signal from the discrete signal. That's pretty remarkable. Now, of course, if u max is greater than 1 over 2 x0, then these copies are going to overlap. And in this overlap region, what happens is that you get new frequencies, and from the overlap region, there is no way to figure out what the original function f of u is in this region right here, because there are many f of u's that would have created the same overlap region. Therein lies your problem, and the creation of these new frequencies is really what is referred to as aliasing. It produces artifacts in images. So that brings us to Nyquist theorem. And Nyquist theorem tells us when we have aliasing and when not. And basically it says that if u max is less or equal to 1 over 2 x0, which is a Nyquist frequency, then you're fine. The continuous signal is well sampled. If u max is greater, the continuous signal is undersampled. So let's say that the signal is well sampled. And so now what do? Well, what we're going to do is cut out one of these copies that we have right here. And that's very easy to do. You construct this function right here, cu equal to x, when u is less than 1 over 2 x0, that is, it's x in this region, in this range right here, and 0 otherwise. And you simply take this function and you multiply it with the Fourier transform of your sample signal fs. That's the Fourier transform of fs. You simply multiply the two and you get a single copy out right here. And now what do? To get the original continuous signal, you simply take the inverse Fourier transform of this fu and you're done. You get f of x. So, aliasing or undersampling produces, as we have established, a variety of artifacts in images. Now, we don't get to control the continuous signal that's falling on the image plane. That depends on the scene that we're exposing the camera to. But it turns out that for most natural scenes, the Fourier transform of the scene looks something like this. It's called the 1 over u fall off. It falls off as a function of u, the frequency. And so one can say that the maximum frequency that we're going to measure in the image and that's going to fall on the image, in the continuous image, is say u max somewhere here. And you want to make sure that your camera actually samples the image at a frequency that is at least 2 times that frequency u max. When you don't, you start getting aliasing. So here is another example of aliasing where you have things looking fine here, but on this curved wall here, brick wall, you see this sort of ringing artifact or moire patterns on it. So now an interesting question is, can you design your camera in such a way that you always avoid aliasing? Turns out that you can. Well, We, of course, have no control over the frequencies that arrive at the lens of the camera itself, because that depends on the scene that you're looking at. And scene could have a variety of different frequencies, perhaps very high frequencies. However, we have some control over the frequencies that arrive on the image plane, the image sensor itself. And so that's what we're going to look at now. There are actually two things that help us with respect to minimizing the effects of aliasing. First is the design of the image sensor itself. Now remember, the pixels on the image sensor actually are areas. They have a finite area associated with them. They collect light falling on, say, for instance, this square area that you see here. So it's not the light falling at a single point, but it's the light falling on an area. So if you think about the image, the discrete image that's being captured, one way to model it is you have a continuous image, which is first convolved with a box filter of this type in continuous domain, and then that image is being sampled to produce the final digital image. So this convolution with the box filter serves to low-pass filter the image. It cuts out the high frequency because convolution with the box filter is averaging or smoothing. So that helps. And the second way one can do this is use an optical filter that sits on top of the image sensor, which cuts out the high frequencies or frequencies above the Nyquist frequency right here. So using these two methods, you can almost guarantee that the image that you capture, irrespective of what the scene is going to be devoid of aliasing.